Okay, in this video we are going to talk about oxidation and reduction reactions in organic chemistry. So let's quickly sort of define these two terms in a general sense. Oxidation is an increase in oxygen content and or a decrease in hydrogen content. And oxidation reactions can really be abbreviated with a bracket and an O in the middle. Reduction reactions are when we have a decrease in oxygen content and or an increase in hydrogen content, and those can be abbreviated with a bracket with an H in the middle, and that stands for reduction. Okay, so I have a couple of examples here. So in this first graph, primarily we're going to be looking at the alcohols out to aldehyde and carboxylic acid. So just to point out the difference here, here we have a primary alcohol and here we have a secondary alcohol. And for both of these graphs, as we go from left to right, we are talking about oxidation reactions. And as we go from right to left, we're talking about reduction reactions. Okay, so a couple things we can notice, right? An alkane in alcohols is an oxidation compared to an alkane. And if I go from an alcohol, that can be oxidized into an aldehyde. Aldehydes can be oxidized into carboxylic acids, and alcohols can in fact be oxidized all the way into carboxylic acids. So when we talk about oxidation reagents, we'll see that there are reagents to go from an alcohol to an aldehyde, and then reagents that can go from an alcohol to a carboxylic acid, and those same reagents work from aldehyde to carboxylic acid. Conversely, we're talking about reductions. We'll talk about reducing agents that can reduce a carboxylic acid to aldehyde, and really some reagents that talk about reduction from a carboxylic acid to an alcohol. So really one of the first things we need to do when we're talking about these types of reactions is being able to determine whether you want to do or need to do an oxidation or a reduction reaction. And this is something that is really taught in general chemistry, and the primary way that's done is really looking at the oxidation state. And that's something that clearly could be done here, right? So we could figure out the oxidation state of molecules and then calculate whether we have an oxidation or a reduction reaction. But in fact, there's a sort of a shortcut, a much easier way to do this for organic molecules. And what we're going to do is we're going to look at the sum, or total the number of pi bonds, rings, and heteroatoms found on each molecule. And heteroatoms, remember, are atoms that are not nitrogen or carbon. We're really going to be looking at and counting oxygen, nitrogen, sulfur, and halogens and adding that up. Okay? When we look at that number, so I'm abbreviating reactants as R and products as P, if that number increases as we go from the reactants to products, that is an oxidation. If the number decreases as we go from a reactant to product, that will be a reduction. And if that number remains the same, that's neither an oxidation reaction nor a reduction reaction. That's what we like to call a functional group transformation. So let's look at a couple of examples here. So looking at this primary alcohol, we can see that we have no pi bonds, no rings, and I have one oxygen. So we'll give that a value of 1. Looking at an aldehyde, I have one oxygen and one pi bond. Remember, a double bond consists of one sigma and one pi. So we have one pi and one oxygen. That gives me a value of 2. So as I go from an alcohol to an aldehyde, as I go from 1 to 2, that number is increased, therefore that is an oxidation. Looking at a carboxylic acid, we have 2 oxygen atoms and 1 pi bond. That would give me a value of 3. So if I go from an aldehyde to a carboxylic acid, again that's an oxidation. Or if I went from an alcohol all the way to a carboxylic acid, we're going from 1 to 3, the number's increased, again that is an oxidation. And the converse is true. If you go from a carboxylic acid to an aldehyde or a carboxylic acid to an alcohol, we're going from 3 to 2 or 3 to 1, and those are reduction reactions. All right, the same is true for alcohols, for secondary alcohols, excuse me. So here's a secondary alcohol, and that can primarily be oxidized to a ketone. One oxygen here, the ketone has one oxygen and one pi bond, that's a value of 2. So if I do an oxidation reaction from an alcohol to a ketone, That's clearly an oxidation reaction. Let's look at an example where this value remains the same, and a good example of that is reactions we've learned before. If we talk about a reaction from an alkene to an alcohol. So here we have butene to butanol. If you look in butene, we have one pi bond, and in butanol we have one oxygen, so I'm going from 1 to 1. So this is not an oxidation reaction, even though I've increased my oxygen content. This is what we call a functional group transformation. And that's really the key here, is that this little shortcut will definitely indicate whether you have an oxidation or not. And here we do not have an oxidation or a reduction. We have a functional group transformation. Because in fact we've increased the oxygen content, but also increased the hydrogen content. So we have one hydrogen here, here we have two. So since we've done both of these, it is not an oxidation nor a reduction. Okay, so let's look at a couple of examples here. We're going to start with oxidation reactions. What I want to point out, the point of this video is really to talk about the reagents and the products formed. I'm not going to talk about any mechanisms in the oxidation reactions or the reduction reactions. So talking about the oxidation reactions here, I have this organized by the type of alcohol we have. So here I have a primary alcohol. Again, what that means is we have an alcohol connected to a carbon, and that carbon is connected to one carbon. So there are two hydrogens here. So these first two examples are both primary alcohols, and I'm going to draw those hydrogens in so we can clearly see that and indicate that these are both primary alcohols. So for sophomore organic chemistry, there's really 5 main reagents that we're going to talk about. First, let's focus on the reagents Pcc or DMP. Okay, these reagents are essentially interchangeable, so I can either use PCC or DMP. And what these reagents do is they convert a primary alcohol into an aldehyde. Okay? PCC stands for pyridinium chlorochromate, and here's the structure here. We have our pyridinium molecule followed by our chlorochromate molecule. A couple advantages of this molecule is it's very cheap. So it's really easy to use. A disadvantage is that it is toxic. So if money is no object, it's probably best to avoid using this chromium complex. Another thing to consider is this molecule is acidic, and that could come in play whether you need to avoid acid or not. Our next example is DMP. That stands for Des-Martin periodinane. And here's the structure of that molecule. Des-Martin periodinane is very expensive, but it works very, very well. So if money is no objective, this is a great reagent to use. It works terrific. And the other advantage here is that this molecule is in fact neutral. So if you had a molecule that was sensitive to acid and you needed to do an oxidation to an aldehyde, DMP would be the best example here. Now for sophomore organic chemistry, we're really not going to get into it that deep. So essentially you can use PCC or DMP interchangeably. Either would work fine. Next, let's look at the next 3 reagents we want to talk about. Chromium trioxide and acid. That's called the Jones reagent. Sodium dichromate or potassium permanganate. And all 3 of these reagents do exactly the same thing. These are much stronger oxidizing agents, so the oxidation of a primary alcohol goes through an aldehyde, but the final product you get out is a carboxylic acid. So primary alcohols are oxidized all the way up to a carboxylic acid, and you cannot isolate the aldehyde intermediate. In fact, the oxidation of the aldehyde to the carboxylic acid is much faster. So the Jones reagent, chromium trioxide, usually uses sulfuric acid, but here I just wrote a generic H+, will form the carboxylic acid. Sodium dichromate or KMNO4 all does the same thing. So these are really interchangeable. The one caveat I'd like to add is that potassium permanganate is a very, very strong oxidizing agent, so there's other reactions it can do. So if you remember, it can also oxidize alkenes, and it can also oxidize benzylic positions, benzylic carbons as well. So primarily the oxidizing agents of choice are the Jones or the sodium dichromate. KMNO4 will do it well, but there are side reactions you have to watch out for. Okay? So there's the distinction between primary alcohols. When we get to secondary alcohols, it's quite simple. All 5 of those oxidizing agents will convert a secondary alcohol. So remember, a secondary alcohol means that this carbon atom is attached to 2 carbons and only 1 hydrogen. All 5 reagents will convert that secondary alcohol into a ketone. PCC, DMP, the Jones reagent, potassium permanganate, sodium dichromate all do the same reaction, oxidize to a ketone. And I just want to point out tertiary alcohols undergo no reaction. So if you notice in the examples of the primary alcohols and the secondary, you have to have a hydrogen on the carbon of the alcohol. Tertiary alcohols don't have any hydrogens. There's 3 carbons here, which is why they're tertiary. There's no hydrogen to remove, right? So if you look at our ketone here, we've removed 1 hydrogen. There's no hydrogen to remove, which means we have no reaction. So tertiary alcohols, if you treat these with any of these oxidizing agents, give exactly the same product. No reaction occurs. Okay, so those are the main oxidizing agents we need to talk about. Let's take a look at some reduction reactions. And here I'm going to organize this a little bit differently. What I'm going to do here is I'm going to focus on 3 reducing agents, and I'll talk about each reducing agent one at a time. So the first reducing agent we're going to talk about is called LAH, or abbreviated LAH. That stands for lithium aluminum hydride. The formula is LiAlH4. And then here's sort of an image of what that looks like. We have a lithium cation, and then our AlH4 molecule has a negative charge associated with it. And again, we're not going to go through the mechanism of this, but in each case we treat it exactly the same. This is a 2-step process. Step 1, you add the LAH, let the reaction occur, and then when you're done, you're going to do what we call an H+ workup. You're going to treat the LAH with a little bit of acid, and here I'm just writing a generic H+, and that's really called a workup reaction here. What we're doing is we're quenching any excess LAH that you have. So now I've got this organized by functional group. First, let's look at our carboxylic acid. Right? Then we have a simple ester, followed by a ketone and an aldehyde. It's very important here to be comfortable with your functional groups. If you're not comfortable with your functional groups, oxidation and reduction reactions can be pretty complicated, or it's easy to make mistakes. So when a carboxylic acid is treated with LAH followed by H+ workup, you get out a primary alcohol. What I want to point out is I want to number my carbons here. There's carbon 1, 2, 3, and 4. And kind of a common mistake students make is they forget that this is actually a carbon. Okay, so I'm not adding carbons, I'm not taking away. We're going to form butanol here, 1, 2, 3, 4. Okay, so LAH will reduce the carboxylic acid all the way down to the alcohol. This is a very strong reducing agent, and it works on all 4 of these functional groups. Next, let's look at our example of an ester. Again, I'm going to number carbons here, 1, 2, 3. Okay, and in this example, it's going to reduce everything into alcohol, but you're going to get 2 alcohols out. We're going to cleave this bond. So 1, 2, 3 becomes 1, 2, 3. Again, we get a primary alcohol, and whatever type of ester, this is a methyl ester, that will become methanol. So if this was an ethyl ester, that was an ethyl group, you would get out E2OH. So again, a primary alcohol when you reduce an ester with LAH. Looking at a ketone now, okay, so a ketone can be reduced by LAH as well, and now with a ketone you get out a secondary alcohol. So essentially what we've done is we've added a hydrogen to the carbon of the carbonyl. Quite simple. We have an aldehyde here. Okay, remember there is an H there. So again, an aldehyde will get out a primary alcohol, 1, 2, 3, 4 carbons, 1, 2, 3, 4 carbons. We get out a primary alcohol, and again, we've now added a hydrogen. So with an aldehyde, there was 1 hydrogen connected to carbon 1. Now there's 2, again, getting out a primary alcohol. So LAH is a very strong reducing agent capable of reducing a carboxylic acid, ester, ketone, and aldehyde, all to alcohols. All right, the next reducing agent I want to talk about is sodium borohydride, NaBH4. Again, here's the structure of that. Very similar to LAH, but instead of aluminum, we have a boron here. Okay? Also similar to LAH is we have to have a workup step. So sodium borohydride is what we add, and then you can either work up with H plus or water. Either of those is fine. So in here I listed both. Now we're going to see a difference here between sodium borohydride. This is a weaker reducing agent, so it is not capable of reducing your carboxylic acid nor your ester. So upon treatment of a carboxylic acid with sodium borohydride, you get out no reaction. What that means is you still have the carboxylic acid. The functional group is not reduced. And that's the same with an ester. Sodium borohydride is not a strong enough reducing agent to reduce an ester, so you're left with the ester as your final product. And this is really the key difference between sodium borohydride and LAH. LAH reduces carboxylic acids and esters to alcohols, where sodium borohydride does not. So I'll draw a big line here for the distinction. When we talk about ketones and aldehydes, well, sodium borohydride does the exact same reaction as LAH does. A ketone is reduced to a secondary alcohol, so this hydrogen here adds an H. And for the aldehyde, the sodium borohydride, again, will add an H. So let's draw in the H of our aldehyde. And now we have 2 hydrogens, again, giving us a primary alcohol. Okay, so for aldehydes and ketones, sodium borohydride is exactly the same as LAH. And that's the clear distinction here. Aldehydes and ketones are more reactive than esters and carboxylic acids, and sodium borohydride is strong enough to reduce these 2 compounds, which are more reactive. It is not strong enough to react with the less reactive carboxylic acid and ester. Okay, there's one more reducing agent I want to talk about. It's pretty specific, and it's called DiBAL-H. That's the abbreviation for di-isobutyl aluminum hydride. Here is our structure below. We have aluminum. This does not have a charge with 2 isobutyl groups and a hydrogen. Now I've drawn this as a monomer. Typically it's actually found as a dimer or a trimer when it's used in solution for the reactivity, but it's simple for us to write it this way. So DiBAL is quite specific. Okay, it's going to react with an ester, and DiBAL-H at minus 78 degrees is able to reduce the ester to the aldehyde. Okay, so again, we're going to cleave this carbon-oxygen bond. So that portion becomes methanol. If that was an ethyl ester, that would be ethanol. But I want to focus on the main carbons here, 1, 2, 3, 1, 2, 3. And that's what this reagent is primarily used for, to go from an ester into an aldehyde. Okay. The key to this, though, is that DiBAL has to treat an ester at minus 78 degrees. So you really have to include the minus 78 degrees here. Again, I have a workup step common for all reducing agents, and here you can just use water to do the workup. And that's how DiBAL-H is really used. The only the best reaction is to go from an ester to an aldehyde. One thing I'd like to point out is if you have DiBAL-H in the presence of a ketone or an aldehyde at room temp, notice it doesn't say minus 78, that will react exactly like sodium borohydride. So a ketone would be reduced to a secondary alcohol, an aldehyde to a primary alcohol. But again, that's not the point of diabyl H. So really, if you want to do these reactions, you wouldn't use diabyl H, you use sodium borohydride or LaH. Okay, so that's really all I wanted to cover in this video. I have a couple problems here, so please complete these 6 problems and bring them into class. Question A, I'd like for you to supply the reagent to convert a carboxylic acid to a primary alcohol. Part B, we have 2 functional groups. We have an ester and a ketone, so supply the correct reagent to only reduce the ketone. Don't touch the ester. For C and D, we're starting with the same reactant. We have a primary alcohol, so supply the reagents to form the aldehyde, and then the reagents to form the carboxylic acid. And for E and F, I'd like you to draw the structure. So here I have a molecule that has a carboxylic acid on one end and an aldehyde. Give me the product when that's treated with LaH. And then here we have a diol, a primary alcohol and a secondary alcohol. Give me the product F when this diol is treated with DMP in excess. So there's enough to react with both alcohols. Turn that into class. And that's it. Thank you.